Chris.
I will not. Welcome to the Monday seminar. It's wonderful to see you all. And we are very lucky today to have Eran Bouchbinder joining us from outside of Tel Aviv. Eran, as you well know, has been working in many areas connected to friction and problems of dynamic rupture. And today he's going to talk on this title that you see in front of you. I send out the formal introduction by email and then like to keep this informal, so I won't say too much more about that. I'll invite you to read the introduction and learn some of the many things that Eran has done over his incredibly successful career. Normally, our mode of operation is to ask people to mute and to interrupt with simple points of clarification. But I understand that Eran would like people to interact more, and so I'm going to let him decide and tell you what to do. But I will ask you to mute at the beginning, at least, just to kind of keep attention on what happens with Eran. We often at the end we have often up to 30 minutes of time to have an extended discussion and question and answer period. And so I will ask people to prepare to involve themselves in that, prepare to participate, because it is one nice thing. This seminar approach, of course, by Zoom, we're all somewhere. It's nothing like ideal, especially for Eran to give a talk into a screen. On the other hand, it allows the possibility of having an extended discussion because people who need to leave will do that. Okay, no more from me. Eran, thank you very much for putting this together. Turn things over to you.
Many thanks, Chris, for running this seminar series, for inviting me, and for the very kind introduction. As Chris mentioned, it's quite discouraging to talk to a screen and to listen to myself. So if you can engage in some form, even just some human feedback, it would be nice just to see that I'm not alone here. And I leave it in the hands of Chris actually to manage time and things like that. All right, so with this, you see my title. Let me open by introducing my collaborators on this project. So, but now, all right, so first, Efim is a long-term collaborator of mine on the more theoretical side of the story. He is in Forschung Zentrum Jülich. Anna, I think she's also here in the audience. She's a staff scientist, permanent staff scientist in my group here at Weizmann. Fabian is now a research associate in Oslo. I started working with him when he was a PhD student with my good friend of mine, Jean-Francois Molinari at EPFL. And actually, the same goes for Thibaut. He's now a postdoc in Amsterdam. Good. So let me start with a classification of rupture modes in the context of earthquake. This is, of course, clear, I'm sure, to anyone in the audience, but I prefer to put things on the table clearly. So the first mode of rupture, I call it crack-like rupture mode. And it actually bears the analogy to ordinary opening cracks. And here you see a crack. I think I can use second laser pointer. So here you see an opening crack, and if this crack extends, so it has a size L that grows with time, then the opening, or in analogy under shear conditions, the slip displacement scales with the size of the crack, and in particular, in this case, rupture size increases with time. That is to say, there is no characteristic rupture size, and the slip at fixed point on the fault, here on the prospective crack line, persists during the entire event's duration. And here I put like in boldface because for these properties, the analogy works. Other aspects, which are not discussed today, the analogy to ordinary cracks is not perfect, but this is not the topic of today's talk. Now, this is not the only mode of ruptures that is encountered in earthquake physics. And if you look at this cartoon, of the Eurasian plate and the Indian plate with this subduction zone that gives rise to the Himalayas. And you focus on this amazing paper that focused on the 2015 earthquake in Nepal. You see another style of rupture. And I guess people know this, but still I love this movie, so I'll show it. This is the hypocenter. Propagation direction is roughly along this 15 kilometers line, and this direction of displacement is predominantly in the Kathmandu direction. And I think I run it. So it propagates for about 70 or seconds. And in this case, this is a snapshot of the movie. You see that the rupture mode is quite different from the crack-like mode. In particular, it's called slip pulse rupture mode. And in this case, rupture does feature a characteristic size. We call it compact support that you see here. Let me put my pointer back again here. And if you now ask the question of the duration of sleep at a fixed point on the fault, it does not scale with the event size or the event duration. Typically, it's much shorter. So we're going to use this classification, and let me focus. Oh, this is probably not for us. Now, it was already mentioned with a pre-discussion with Chris. I think historically, Chris mentioned earlier discussion in the earthquake literature, but I think this definitely an important point in time. This is the Thomas Heaton 1990 paper discussing the relevance and implication of self-healing pulses. Since then, there was a lot of observational, numerical, and theoretical work on sleep pulses, which I'm unable to review here for lack of time. Let me mention that in the context of mode 2 fracture, not necessarily friction, there were solutions that are relevant. For example, the mode 2 version of the famous Joffe problem, then the Broberg analysis of the late 70s, and Friend's 1979 solution, which appears here in bold because Heaton actually discusses this solution in his analysis. And again, I'm not showing any direct observational data, but just a few statements from papers. So from this paper, it is stated that several lines of reasoning suggest that natural earthquakes occur in the self-healing rupture mode. This is from this paper by Dunham. And very recently, I think a week or 2 weeks ago, this PNAS paper discussing a laboratory experiment, they state at the very beginning that we consider a sub-Rayleigh pulse-like rupture as a suitable reference because it represents the typical rupture observed in large natural earthquakes. So this is just to say that this mode of rupture is apparently relevant. So what is the physical origins? And there are many, I list several of them here, of these modes. Let me start with this cartoon. So what I call rupture front, actually, and I disregard singularity and things like that that will emerge later, I would say that this is an object that propagates at some velocity here from left to right. And it's a sliding state, slip velocity finite, larger than 0, that invades a region which is almost locked. So it can be strictly 0 or creeping very slowly. When you talk about these kind of solutions, generally, you should consider the possibility of having what we call the inverse front or the healing front. In this case, again, the solution propagates, the object propagates from left to right, but in this case, it is the non-sliding state that invades a sliding state. This is why we sometimes is called in condensed matter physics, the inverse front. And now the point is that if these two objects interact either through the interfacial constitutive relation, so the contact interface, and or through elastodynamics of the bulks that form the interface, they might lead to such an interaction that will select a characteristic size. This is the compact support L, and a characteristic propagation velocity. where in this region, the slip velocity is significantly larger than outside. And if this is the case, the crucial point I would like to highlight is that it means that near the trailing edge, you have frictional strength increase. Some people term it relocking, some people call it strength recovery or re-strengthening. But there has to be some physical mechanism that takes these regions when the pulse goes by and put it back into the non-sliding state. So what can cause this? And I'm going to list a few possible origins. The first is geometry. I also listed heterogeneity. I mainly focus on geometry. And actually, this is believed to be the case in the Kathmandu earthquake example that I gave. In this case, it is thought, and actually there's quite a lot of evidence, that there is a finite seismogenic size here along the subduction zone where you have two aseismic stable regions below and above it. And it is this length scale that makes this problem sort of analogous to the strip geometry of fracture mechanics. And this length scale selects, actually in this case, the size of the pulse. This is one possibility. Another possibility is related to the existence of dissimilar materials, sometimes termed bimaterial faults. And in this case, if you have a blue material and a gray material, which feature different elastic properties, it is known that the normal stress is coupled to the slip. In particular, it can be reduced. And if it is reduced over a certain length scale, it may favor this kind of solutions, slip-like. The important names appear here. And just to mention, and I know Jay is here in the audience, this is an active field of research. So a very recent paper actually focuses on the similar materials and on the slip pulses mode that is inherited from this mechanism. Yet another possibility is actually related to the interfacial constitutive relation. Here, I would like to highlight this late 1990s paper by Perrin and by Zeng and Rice, which actually point out two mechanisms. One is re-strengthening under stationary contact, that is to say contact aging and the evolution of the structure of the interface, the contact area. And another one is sufficiently strong velocity weakening friction. They can work each one of them or the two of them together. And this is yet another possibility. Now, even if these exist, this does not necessarily mean that the slip pulse mode will be selected. It can still be crack-like, and that might depend both on the background stress and on the nucleation conditions. In this talk, I'm going to focus on these two. That is to say, I'm going to adopt the following assumptions. We consider infinite homogeneous bulks and planar homogeneous faults. In some sense, these are simpler than the other two that involve either the bimaterial effect or some finite geometry. Now,
Eran,
yes, sure.
I'm sorry to interrupt, but maybe in the spirit of making
Great.
you not feel completely lonely, will you say a little bit later or now something about how number three, because the two things that are listed there both correspond to cases that wouldn't be a nucleating dynamic rupture, right? Like, the strong velocity strengthening case. Or, oh, sorry, I'm sorry, I read, okay, strong velocity weakening. But the re-strengthening under stationary contact, how does it start? How does it stop to begin with to make it?
How does it, I missed the question. So how does it?
How does it stop slipping?
So again, this is the point that if you have such a solution that the stress drops and it facilitates enough re-strengthening, then it might lead to this. Formally, in mathematical terms, if velocity weakening is not strong enough, this is really a necessary condition. It's a necessary condition. And later on, if I go back to these papers here, yeah, so originally it has been pointed out that re-strengthening is a necessary condition, but then it was realized that if velocity weakening is strong enough, this is not necessary.
Gotcha.
But again, as I stressed, this is, even if you have these conditions satisfied, it means that it is possible to excite sleep pulses, but it still depends both on the background stress level and on some details of the nucleation process, which I'll highlight soon. Okay?
Gotcha. Thank you. Thank you.
Thanks for the question. Okay, so as I mentioned, we focus on this. We put aside finite geometry, any heterogeneity, and any contrast in the material property across the fault. And now we would like to adopt a minimal interfacial constitutive relation. And by minimal, I mean simple, but not too simple. And here I would like to highlight what I mean by that. So, and each one of these items have a lot of laboratory support, including by Chris and others in the audience for sure. So the first is the intrinsic rate dependence of frictional strengths, which is going to be a recurring theme also in the second part of the talk. Then there should be, as we just discussed, some evolution of the structural state of the fault, if you like, evolution of the real contact area under both sliding and stationary conditions. So there should be some mechanism of rejuvenation under sliding and aging in the absence of sliding. And the transition between no sliding and what we call stick and sliding, which we call slip, has to feature a characteristic slip displacement. I would say that these are the sort of minimal generic properties of a friction law. Of course, many other effects, pore pressure, and many other, and gout, etc., should come in if you'd like to be more and more realistic. But from my theoretical physics perspective, these are the minimal, these are the core. And that means that the frictional strength, denoted by tau, should be a function of the slip velocity and some other scalar field that characterizes the real contact. Here it is called phi. This is not crucial what it is exactly. And if we do adopt this phi, then its evolution is given by the Dietrich or the aging law, with this characteristic distance that actually controls the transition between no sliding and sliding. And you see immediately here with this one that if there is no sliding, still there is an evolution of this of the contact area because of creep, even in the absence of shear sliding. All right, so now what do we choose for this function? About 10 years ago, we compiled a large data set of experimental data. Let me focus on this one and zoom in. This is a highlight example for two different normal stresses. This is the steady state frictional resistance as a function of steady sliding velocity. And you see that it generically has this N shape. And of course, you notice that we stop here at millimeter per second in this laboratory experiment. But if you go to significantly higher, you can definitely have additional weakening at very high slip rates, which is also established. So you would say it's actually an M-shaped. This is, again, not crucial for the discussion. We actually adopt this N-shaped steady state friction velocity, friction, the dependence of friction coefficient or frictional strength on the velocity. And then, of course, we need to couple this constitutive, interfacial constitutive relation to the bulk, which will introduce the effect of the background stress and of some dynamic nucleation conditions. This is done when we consider two infinite bulk by the elastodynamic Green's function, so you can reduce the problem into just a one integral equation on the surface. This is frictional resistance, and it is balanced as a boundary condition by the right-hand side, which features the background stress or the driving stress, which is here constant, the so-called local radiation damping term, which is proportional to the local slip velocity, and all the complicated spatiotemporal interactions are buried in this convolutional integral that in general does not even have a real space and real-time representation. This is the long-range in time and in space interactions that are mediated by the bulks, the linear elastic bulks. Now, I said that rupture modes can coexist. What do I mean by that? I mean that for a given fault with a given constitutive relation, you can either excite rupture-like modes or slip pulses. And we discussed this in this paper. It should be important to note that very similar analysis has been performed earlier by Gabriel et al. This is a phase diagram where here on the x-axis you have the background stress, the same tau d that we just introduced. And here L, forget about the normalization, is just the typical size of the nucleating patch. And here we have a rather comprehensive phase diagram. I do not want to discuss it. I would just want to highlight the following point, that if we fix the background stress, we can have for the very same fault, the very same homogeneous fault, both expanding crack-like rupture, if at this fixed background stress, the nucleating patch is above this blue line, or a slip pulse that we call sustain, and this word is important and will be clarified a bit later. Let me actually show you these modes. So I'm going to show you a simulation done by Fabian. I think I should again remove this pointer, and I'm going to run it twice. First, feed. So this is an expanding crack-like object. It is done under mode 3 symmetry conditions. Let me run it again and just stop it very early. So we introduce into a nearly non-sliding, this is V-stick is extremely small velocity, a perturbation of this size, and this is the evolution of the perturbation. You see it leaves behind a sliding state that invades as the two edges propagate in opposite direction. Now, the very same fault, everything is the same, the very same background stress. If we just introduce a slightly smaller initial perturbation, and I'll stop it now at the very beginning, it is slightly smaller than the one that you saw before, and look at the outcome. It starts as if it would like to be a crack, but actually a healing front that was just discussed develop, and an object that we call sustained slip pulse propagates. Let me run it again because I think it's rather illustrative. Here the healing front builds up and it propagates. Whether it's steady state or not will become a central question, but it is sustained. It's sustained in the sense that it preserves roughly its velocity and shape over relatively large propagation distances. Now, this, let me highlight here a methodological aspect of this result. It goes to Jean-Francois Molinari, a good friend of mine, already mentioned at the very beginning, and Thibaut and Fabian, along with Philippe Jobel, who developed this open library called Cracklet that allow this dynamic calculation. It really shaped our research over the last few years. All right, let me go back to the pointer. And with this, it was quite long, but I think hopefully useful. I would like to list the main questions that I would like to address in the next 35 minutes or so. So the first question, what are the properties of steady state slip pulses? And in particular, are they stable? The second question is, what is the equation of motion of frictional slip pulses? And are steady and unsteady slip pulses intrinsically related? The third question, not really introduced so far, this is why it appears in green here, is related to the singular nature of the near edge fields of slip pulses and actually also of crack-like ruptures, and what are the implications of the singular nature on the earthquake energy budget. So this is sort of a complementary topic that I hope to discuss towards the end. But let's start with the first blue questions. So we already listed the equations and what it amounts to find steady state slip pulses. So these are the full dynamic equations that are actually solved by Cracklet that we just introduced. And looking for steady state slip pulse solutions amounts to the following. First, you ask these equations, do they have solutions in which space and time are constrained to appear only in this psi form with some a priori unknown propagation velocity c pulse. So it's not that x and t can be independent. We are looking for solutions of this moving combination. Under these conditions, this complicated equation becomes somewhat simpler. The entire elastodynamic interactions appears here as a Hilbert transform of the slip velocity. Details are not important. This curly f is a known function of the unknown propagation velocity. And we need to impose boundary condition that will distinguish crack-like solution from slip-like solutions or slip pulse solution. And these are the boundary conditions that just mean that far ahead of the region of interest, you have vanishing slip velocity, both ahead and behind. If you select this, this is a solution. And a solution actually amounts to finding this v of psi and phi of psi, two fields, and the unknown propagation velocity. Let me highlight here that unlike previous solutions, our v is continuous. We don't impose v equals 0 by hand in certain regions of space, and we don't constrain any singularity. There was from previous solutions where you say this leading edge should be singular, but here you should have no singularity. We don't constrain anything of that type. And note also that the compact support, the pulse size, is not part of the formulation. There is no letter L in the solution here. If such a solution emerges, we can extract it just by defining the characteristic size. This was a long story, but essentially we found these solutions. This is one example. We find a family of them as a function of the background stress. Now, in the plane of v and phi, these solutions actually form closed circles because you need to re-strengthen. You need to go back to the relocked state. So you go along this direction, you have the sliding region where v is large, but then you go back at the tail. And it's almost closed. This really depends on how tough you are numerically. And of course, since the stress, the frictional resistance is just a function of v of phi and v, you have these circles close, it's not, they're not circle, close orbit also in the stress and slip velocity plane, and the different orbits just correspond to different background stresses. Good. Let's now look at the properties of these solutions. Two of them are highlighted here. First is just the propagation velocity, normalized by the shear wave speed, which is just beta, and the size that is visually defined here. And you can ask how they vary with the background stress. And you have here the propagation velocity on the left with the circle and the size with squares with the right y-axis. And they both grow quite significantly as you approach a special background stress that I do not discuss here. And actually, the green lines are theoretical curves that I do not discuss either. The important point is that you have these solutions, and in principle, you can construct a curve which relates the propagation velocity, and the superscript 0 just means these are steady state solutions, that depends on the size. So there is a size velocity relation that is parameterized by the background stress. And you walk along this line as a function of the background stress. Fine. So we found this solution, and the next question is the dynamic stability of these objects, because we imposed steady state condition and ask the equations, do we have such solutions? But whether this solution will be realized in nature and in the lab, it really depends on the stability. Whether this assumption that solutions with this co-moving coordinate actually realized. For that, you need to perform stability analysis. We are not the first to ask the question. I already mentioned this important paper by Perrin, Rice, and Zhang. They somewhat address the question in the conclusion, or maybe in the abstract or both. They state this analysis suggests that the strictly steady traveling wave pulse solutions may be either unstable or have a limited basin of attraction. jumping ahead quite a few years to the 2018 paper that I already referred to, we studied this problem in what is called the elastic slab configuration. That is to say, not the infinite system, but actually a finite and small height system. And we actually show that indeed these steady pulse solutions are unstable. Soon after us, a very important paper by these authors emerged, and they studied pulse-like solutions for the thermal pressurization, a more realistic constitutive relation, and they also studied the stability by actually perturbing the background stress. So the perturbations were just homogeneous perturbation in the background stress up and down, and they also concluded that sleep pulses, for their constitutive law, are intrinsically unstable. And this is what we did last year. We took our steady state solutions, we removed the constraint of imposing steady state, and we introduced perturbations not in the background stress, but actually something which is more intuitive, either slightly expanding the size or slightly contracting it. And then we follow the full time dependent dynamics after the introduction of this perturbation. And this is the generic answer. Here on the x-axis, you see time. And here there are three properties of the pulse: its size, normalized by the steady state, the initial size, the propagation velocity, and the maximal sleep velocity. They all start at 1 by construction. But what you see is that if the perturbation is slightly larger, so you slightly expand, you become unstable. Size growth, it accelerates, and sleep velocity increases. And if it is slightly smaller, so the perturbation is a slight shrinkage, then pulses die off eventually. So we conclude, in line of the earlier indications, that steady state sleep pulses are actually intrinsically unstable. In the language of first order phase transitions, they are like critical nuclei. So just for those who are not familiar with this, if you look at the solid liquid transition, you actually ask the question of under what conditions a critical crystalline nucleus can be found in the metastable liquid. And if it is small enough, it die off like the blue one. And if it is above a critical size, which in this analogy is the steady state pulse size, it grows. And in the other problem, the crystal grows. So this is the analogy. But then you ask the question, which is crucial. So you know these solutions are unstable. Are they useful, or the other way around, are they useless and should be completely discarded when you actually discuss unsteady pulses? In principle, if you are categorically unstable, these solutions are not very useful. So you impose steady state conditions, you fund the solutions, but they will not be realized. But then we have second thoughts. I'll try to walk you through this. So now we are looking at the dynamics of unsteady sleep pulses, which is the general case because we know steady state pulses do not exist. Here is the sleep pulse, one of them that I showed you, and here I highlight the three properties: size, propagation velocity, and maximal sleep velocity. I put the initial condition, which is the steady state solution, and I plot it in a plane where we have the size of the object as a function of the propagation velocity. And in this plane, the steady state pulse put there on time equals 0 is just a point. And the question now about unsteady dynamics is what happens if you now remove the steady state constraint and run the full dynamical evolution of the system? What will this point do? Now, in general, it will just plot some line, very complicated in the plane. And that's actually the question. Is there a generic line, which we call eventually an equation of motion, that exists in this plane? And what is special about this plane that needs to be discovered? And here is our idea. So first, if you remember, I have solutions not just for this particular background stress, but actually for any. So now I This is one solution for a given background stress tau d, but I can plot the entire velocity size relation in this plane. It is this curve. You should ask why other background stresses are relevant. If I fixed, the answer will come soon. Now, we already found that this point cannot stay in its place. It's unstable, so it will move. And we know that if it is slightly larger, it will move up, increasing the velocity and the size. And if it is slightly smaller, it will go down and die off. One can argue, and I won't detail the argument, that this evolution goes along the tangent. There is one direction which is unstable, but the other direction is actually stable. It's like a saddle. If this is the case, and then you move to another point, it does correspond to another background stress, but this point is also unstable and also has this feature that evolution goes along the tangent. So our hypothesis was that maybe the dynamic evolution of unsteady slip pulses will be constrained to this line. And we set out to test this hypothesis. So first, we just took this point, slightly perturbed it as small expansion or small contraction, and that was the rather stunning finding, that indeed the growing pulse follows the steady state line of other background stresses, and the decaying one very closely follows this branch of this line. And then we tested to many other cases. Here you see 9 difference for different points along this line, and this was the general case. If you perturb slightly above the steady state point, you grow. These are the hot colors, or you decay if you're slightly smaller. Now, there was a question of how fast I move along the line. Because if these unsteady slip pulses that you already saw, both in nature and in computer simulation, they exist for long times, it means that in some sense the instability should be slow. The way to quantify it is just to look at this dimensionless quantity, which is the rate of change of the size of the pulse in units of the propagation velocity. If this is small, it means that it retains its properties while propagating many times its size. And this is what we call sustain. And we find out that indeed this is the general case. When you have growing pulses, they grow with this dimensionless number much smaller than unity. So we conclude, yeah, there was a question.
I'm perfectly happy to just wait until the end, but again, going back to the idea that it might be more fun to interact.
Yeah, go ahead.
You showed us that case where for your N-shaped velocity, your friction velocity curve, you showed us a case where there was a slip pulse and where there's not a slip pulse. Does that apply also to this case here, where you talk about background stress, or is that really a separate?
That's a very, very good question that I'll actually touch upon soon. But just to answer explicitly, everything here is done for objects that remain pulses. That is to say that you can meaningfully represent them as a point in the plane of velocity and size. Now you ask, for example, what happens if they are crack-like to begin with? They are not here by definition. An even more interesting question that I will touch upon soon is what happens if you have dynamic transition. So you go out of this plane. But you are absolutely right, that whenever we have a point here, it means that a pulse exists because I can actually represent it as a size and velocity. Okay?
Gotcha. Thank
Great
you.
question. Okay, I see that most. Yeah, you should. If I can see you, it will be even.
Sorry. Yeah.
Yes. Hi.
Thanks very much. So you're talking about the change in propagation velocity and size. What's happening to the shape of the pulse?
Yeah. Okay. Yeah. So roughly speaking, it remains very similar, but changing mostly the size and the velocity, and I'll show you more on that. Again, great question. I already see from time that it is possible that I won't get to the unconventional singularity part, but That's absolutely fine. I really like you to be engaged and that whatever I say will be understood. At least what I wanted to say is understood. So just
Eran, I
yeah,
could ask a question. I could ask a question, or I could wait till the end.
go ahead. Nice to meet you, Eran.
So we have intuitively, or experience or intuition or whatever, numerical simulations suggest that if you have in the crack-like world, if you start with a nucleation zone which is larger than the critical value, you rapidly increase toward the shear wave speed. And what you have on these plots here are, a full range of steady state solutions where the propagation speed is a very small fraction of the shear wave speed.
Yeah.
And intuitively, I would say that to have a steadily propagating pulse at 10% of the shear wave speed seems like it must be very finely tuned. So I guess my intuition would say that if you have propagation speeds which are a very small fraction of the shear wave speed, somehow those steady pulses must be much harder to access than pulses that are close to the shear wave speed. Is
Okay,
that?
so let me clarify this. So first, we just showed that there are no steady state, okay?
Yeah, okay. Yeah.
Now, you are right that typically those that feature these small velocities are decaying. They indeed die off following your intuition. And those that grow are typically in the upper side of the velocity curve. So I don't think there is any immediate contradiction to your intuition, but what I can assure you is that nothing is fine-tuned here. So what I showed you here, you start, again, let me follow the procedure. You start, for example, at this point, you put your steady state crack and you remove the condition of steady state. You will follow just the dynamics. In this case, if you slightly increase the initial pulse, it just accelerates along this line. And if you slightly shrink it, it will die off along the blue colors.
Yeah,
That
okay,
is okay?
Yep. And in fact, I understood that when you spoke, and then I misspoke my question.
Great.
But I guess so my intuition would say that if you start near, somehow the rate at which you leave your initial solution, the rate at which you leave the steady solution somehow seems like it should be fast if you're
That is the crucial point. It's not fast. This is exactly what I wanted to highlight. It is
even if the sliding speed, even if the propagation speed is a small fraction of the shear wave speed, you still depart from that solution slowly, is what you're saying.
Yes, relatively slowly. All of these growing pulses feature this dimensionless ratio being, and it just means, as I highlighted here, we call them sustained because they are not steady state. However, they do propagate long distances relative to their characteristic size. They propagate many times their size without appreciably changing the properties. They do, and that was. Let me go back to this movie that I already showed. That confused us for years because, and this is also related to Jessica's question. So the shape of this object, this is just general, it was just excited dynamically, no steady state here at all. The shape looks very similar to steady state. It propagates without appreciably changing properties, neither the size, nor the propagation velocity, nor the peak slip velocity, yet its size is not really related to the steady state solution. So we knew it is related, but it was very different. And now we understand why. Because they actually corresponds to steady state solution that just at rather different background stresses through this mapping. That was the crucial point. And let me show you the generality of this result. Let me bring back the pointer. So
Eran, let me just say that you control how quickly you move or not, but don't worry about there's not a deadline.
okay, fine.
Yeah.
Let's agree that I'll finish the first part, and if there is time and interest and audience, I'll say at least something about the exciting part, which is the next. But I really like the discussion. So good. So now let me pose the question of the generality. So we have here what we call an equation of motion, like for ordinary cracks, the friend equation that relates the size of a crack to its propagation velocity, but in some sense, we call this the reduced dimensionality description. So we took two fields and a velocity, and we projected them on a plane with just 2 degrees of freedom, size and propagation velocity, and we found this special line where all dynamics are localized. Now, everything that I showed you so far, also in response to Ellen's question, so far we started with a solution that was put on the steady state line. But of course, if you have just a general nucleation, there is no reason that it will reside to begin with here. It can be anywhere in this plane. And the question was, what happens in this case? And this is what happens. Let me walk you through. So we nucleate dynamic slip pulses using the phase diagram that I showed to begin with. No steady state. The notion now does not exist, not as an initial condition and not later. Just points. And again, related to your question, Chris, what you see here, these 6 initial pulses, they are pulses. So if we did some nucleation and a crack-like object was generated, it is just not here. So for this, and you see that you start generally arbitrarily far from the line. However, quite quickly, all of them were attracted to this special steady state line. And when they hit it, if it is above the steady state point for this background stress, they became growing pulses. And if they hit it slightly below it, except for this small deviation that you see here, they become blue, that is to say they decay. And going back to the question of the evolution of the instability, all the growing one, the hot colors, feature very small dimensionless ratio, which means, again, they are sustained, okay? That means that the conclusion here, which is quite striking, is that this steady state line, L naught as a function of S of Cp, where superscript 0 means the steady state solution parameterized by the background stress, is a dynamic attractor, even though each point is unstable. So it will never remain at the point, but you have a saddle which expand, and then you are being attracted to the line, and once you hit the line, you are there. Either decaying along the line or growing in a sustained manner. And now, yet pushing it farther about generality, this means that there is just single slow unstable mode that goes along the line. But we are talking about fields. They have formally infinitely many degrees of freedom. In this picture, also inspired by first order phase transition, you might imagine and speculate that this single slow mode actually controls all other variables. They are slave to it. To test this idea, we go back to the slip pulse solutions. Of course, it's a field. It has many degrees of freedom. We selected just 2 properties, size and propagation velocity. The question was whether we can take other 2 properties, for example, size and maximal slip velocity, put them on the plane, and whether everything persists. And the answer is definitely yes. So here you see the same solutions, but this time plotted on the plane where the axes are size and maximal slip velocity. The same picture. It's really a 2-dimensional, and that means that this slow mode is unstable, it evolves slowly, and all other degrees of freedom are slave to it. Okay, I promise to get to this. This is related to Chris's question. Everything that I showed you so far is kind of neat, but then there was a question actually raised by a referee. What happens if the background stress is not constant? Everything that we did so far, just remind you, these lines, for example, they were parameterized by a specially homogeneous background stress, okay? The question was what happens, or to what extent this picture persists if the background stress is not homogeneous, in particular whether it has gradients. As a first step towards answering this question, we considered stress gradients, background stress gradient that are slow. Slow in space. What do I mean slow? They vary rather slow compared to the characteristic size of the pulse. And then we ask the question, how does the pulse interact with this background stress gradients? And to what extent this very neat picture of the equation of motion in this reduced dimensionality space, say the LCP space, still captures the dynamical evolution of the system. I won't get into a lot of details, but let me show you two results, one of them related to Chris's question about the transition, the possible transition, dynamic transition from pulses to cracks. So first, an example that during the interaction with the stress gradients, the pulse remained a pulse. And we were able to understand conditions under which, for example, for the oscillatory, so when you have just periodic variation of the background stress, the pulse actually equilibrates in the non-equilibrium sense with the background stress, and in the plane, it actually forms a limit cycle, which still remains close to the steady state line. So in this sense, the reduced dimensionality description still holds even in the presence of background stress gradients. Under other conditions, the pulse tries to stick to to do something dynamic, but then it dies off, and we can characterize these transitions. Now, there's still a possibility that the interaction with non-homogeneous background stresses will lead to crack-like objects, and this is the example I would like to show you here. So this is the initial pulse, and it propagates. Here I plot, this is the space-time plot, and the initial pulse propagates here. This is the self-healing tail. In the presence of gradients like this, we found cases where secondary ruptures nucleates not at the leading edge, but at the trailing edge, and it propagates backwards. So we have back propagating rupture. It also has a forward propagating rupture that actually runs faster than the initial pulse. They merge, and eventually you get an asymmetric bilateral crack-like rupture. I'm showing this example for two reasons. First, it is related to Chris's question. So once this happens, you are no longer in the plane. You have something, you have composite objects and eventually crack-like, they're not in the plane. I didn't anticipate Chris's question, but I think it addresses it to some extent. The other reason is that this brings us to something that we will not discuss today, but it gives you a sense that sleep pulse dynamics and some interaction with long wavelength heterogeneity might lead to some form of sleep complexity. By sleep complexity, I mean you start with a relatively homogeneous fault and you generate a broad range of events in terms of size, the amount of sleep, etc. Good. So I actually finished the first part, the larger part. And would it be okay if I take a few minutes just to introduce the second part, Chris?
I think so, for sure. I think.
Okay. Okay. So there
Proceed.
were a few questions. So even if we are strict about the time budget, I can have 10 minutes.
And the
See
people
how.
know they're encouraged to interrupt with questions.
Okay.
So
Many thanks. So at this point, I would like to raise a related but slightly different question about the edge singularity of earthquake rupture. And as you see, it will be valid for both sleep pulse ruptures and crack-like rupture. So if I look at the sleep velocity field and the frictional strength or interfacial stress fields for a rupture front, this is actually a pulse. You see it's a pulse because it goes back to the very small velocity at the tail. It propagates from left to right. And a generic property of this rupture front is that ahead of them, the stress features some singular variation of the stress. And behind the propagating edge, the slip velocity features power law decay, singular-like behavior. If there were strict crack, that will be just 0 and jump and a singularity, and the same for this. Here we have real interfacial constitutive law, so everything is smoothed out on a small length scale that we'll discuss in a second. Now, what is the power law here? What is the singular power law of the stress and of the slip velocity? And they go hand in hand together. So it is commonly assumed that the stress singularity is the famous, the celebrated square root singularity power law of ordinary cracks, which follows linear elastic fracture mechanics. This means the disk psi is -1/2 in this case. And this might be a good approximation, it might be less good approximation, but we were able to understand and elucidate under which condition it is and how it deviates and what are the implications. And I won't go through the math, but actually give you the main physical insight. What we were able to show that in general, if you have rate dependence of the frictional strength, and we already agreed that rate dependence of the frictional strength is the generic properties of frictional interfaces. In this case, the universal singularity of linear elastic fracture mechanics is not valid. The degree by which it is not valid actually depends on the magnitude of the rate dependence. So we were able to show in this pair of papers that in general, the singularity might deviate from the LEFM singularity by some amount. And this amount, which is called delta psi here, is non-universal. And it depends on the rate dependence of the frictional strength, the constitutive law. And if it depends on the rate, it means that it also depends on the rupture velocity, on the dynamics of the system. And it's non-universal. And it might even vary along the propagation. If the velocity of the rupture varies, it might vary dynamically as well. Let's try to better understand this and the implications. First, an example. So we took one of the slip pulses that I showed you before, and we plotted both the strengths minus the minimal residual stress in the interior of the slip pulse and the slip velocity, here normalized by the shear wave speed, but we plotted them since they appear on both sides of the edge. We took the absolute value with an estimate of the position of the edge, and we look for the best singularity. And the best singularity is close to -1/2, but it actually deviates by about 10% for this solution. And this is for the relatively weak rate dependence that you saw in the N-shape friction law, where all rate dependence is both in the weakening and in the strengthening is logarithmic. So it's not very strong, and indeed the deviation is there, but not very strong. The same has been demonstrated for crack-like rupture. The implications differ somewhat because of the size of the rupture, which can grow or not grow, depending whether you're crack-like or pulse, but the feature that you could deviate from the LEFM singularity is shared by both classes or both styles of rupture. Now, let's look at the implications, and in particular, the implications for scale separation. I would be more precise, dissipation scale separation, and the accompanying earthquake energy budget. So we consider this expression for there are many names. I apologize for this. I know that Massimo is not here. He wrote to me, there are many names. I prefer not to give names. Some people call it the breakdown energy, but it is absolutely well defined. Okay, it's the integral of the strength as a function of slip displacement between 0 and the current slip displacement once the residual assumed to exist has been subtracted. And you can measure this. If you do this for an ordinary crack or for a frictional crack that has a well-defined frictional residual strength, the picture is the following. The singularity is -1/2. it means that there is no correction, it is 0. Then you accumulate dissipation on top of the residual stress until you reach the fracture energy. And this happens at the cohesive size zone, the size of the transition between sliding and no sliding. And since this point, the dissipation on top of the background, so background means that the frictional dissipation against the residual, which is there, but it's constant, then you are just stuck at the fracture energy, which is the edge localized dissipation. And this is the picture of ordinary cracks. So you have scale separation between the cohesive zone, in fracture it is called the process zone, and the large scale properties of the problem. And if you continue to calculate this integral, you just get no additional contribution. And why is that? It's trivially because the strength actually relaxes to the residual. The residual is a well-defined object, and if you're above the slip displacement that corresponds to the cohesive size, here denoted by curly L, you just get the fracture energy, the edge localized dissipation, and that's it. Now let's apply this definition to the slip pulses that I showed you before, and we already know there is a slight deviation there from the -half singularity. And this is the answer. They differ in their background stress that we know imply different in size. So when they're rather small, so first, note that all curves at small displacement collapse, and if there is a deviation, it deviates at the fracture energy. So fracture energy remains absolutely well-defined quantity. It is where all curves overlap. Then you see deviation that depend on the velocity, the propagation velocity, and the size. For the largest deviation appear at the largest pulses and the fastest. And deviation can be very large, by hundreds of %, even though the deviation from the singularity was relatively small. The reason is that this actually amounts to an integral over the entire pulse. And even if you have small deviations, they are accumulated and give rise to rather large deviation when you consider this breakdown energy. And this just means that there is no complete relaxation to a well-defined residual strength. In order to account for this, people already in the literature introduced this variant of the breakdown energy where they do not commit that a residual exists, but they just use the current value for the integration of the strengths. And if you adopt this and you accept that the singularity can deviate from -1/2, you get a general expression. Of course, fracture energy is still well defined. If you are at the slip displacement that corresponds to the size of the cohesive zone, you get the fracture energy, the edge localized. But if the singularity index or order differs from -1/2, then this power does not vanish and it continues to grow. Okay, you see if you substitute here -1/2, this is 0, and you just get a constant fracture energy, and it means that here you get stuck at this value, which is the ordinary LEFM case. If you have these small deviations or large deviations, they manifest themselves in a growing breakdown energy defined here with displacement. And if you calculate, and the entire theory, including universal, non-universal, but asymptotic fields, energy release rate, all quantities that are known for ordinary fracture mechanics can be found in these two papers. I do not go over them. I'd like just to focus on this prediction because it's directly accessible. It doesn't involve any fit. It's actually a deviation from a constant. So it's very robust, very generic way to sense the deviation from the LEFM singularity. If we apply this to our pulses, this is just one example. You see that you have the fracture energy, then it's not a constant, but it grows as a power law. This power law is this value, which corresponds to psi, which is 0.4. Again, values are not crucial. And then you can apply it again and again. And if you look at the literature, either for laboratory experiment or geophysical data, you see that it's there and people actually identify this. So just a few examples. This is a very important paper by Rob and Dimitri. They asked about weakening that is related to thermal pressurization. They actually found solutions, and their solutions feature an unconventional singularity of this magnitude, which translate to this power being 2/3, and they noticed it. A subsequent paper, also by Rob and Bruntut, considered not thermal pressurization, but actually flash heating. And yet again, they found another non-unconventional singularity that goes hand in hand with a different growth of this breakdown energy. And just to conclude, this recent laboratory experiment from the group of Marie Violi at EPFL, they actually looked after our papers were published for these unconventional singularities in their experiments, and they claim by calculating, this is, sorry for the notation, it's actually the same objects as you see here. They use just this work breakdown. This W is for work, BD is for breakdown. But they also claim to find deviation from a constant, which implies an unconventional singularity, which have all the implications that I mentioned. So with this, I finish. I can walk you through this, but I think I can very quickly. We discussed first the first and large part of the talk focused on sleep pulses. We concluded they are intrinsically unstable. They actually, the steady state one are like saddle configuration, like critical nuclei in a phase transition. Yet the development of the instability is slow, such that growing pulses are actually sustained. This is why they actually realized in experiments and in nature. They preserve their properties over large propagation distance, many times their characteristic size. The dynamics of unsteady sleep pulses actually follow this line of steady state solutions in a 2D plane. And this line is actually dynamic attractor, even though each point on it is unstable. So you will never stay there, but you will be attracted and remain close to the line as you evolve, either if you grow or if you die off. We also started discussing the implication of introducing non-uniform background stresses, show that whenever sleep pulses persist, they are approximately described by the same general picture, but there are surprises like spontaneous transition to crack-like rupture with backpropagation rupture that nucleates the healing tail, etc. And finally, we discussed the nature and the order of edge singularity, both in sleep pulses and crack-like rupture. The claim was that once you have rate dependence, you deviate from the LEFM singularity. You can be close to it such that the approximation is good if rate dependence is weak, but in general, as in the case of thermal pressurization and flash heating, you can deviate quite substantially, and this has quite important implication for the dissipation scale separation and for the energy budget. And I think I have here, yeah, I mean, if you're interested in many details, this is just a list of references that might give you answers. Of course, you can contact me, but let me go back to this. And with this, I really would like to thank you. Thank you for engaging in the discussion. It was not that bad to talk to the screen.
It was really a fabulous talk, Eran. Thank you so much for doing that. I will invite people to unmute, do as you like, and join me in thanking Eran for a fabulous talk. And we really do have, we have time for a discussion. So please use the raise hand feature. It's the easiest thing to do. I'm sure you're all used to it, but yeah, that's what it looks like. If you're not, if it's at the bottom of my screen, I assume it's at the bottom of yours. And yeah, let's give Eran a chance to catch his breath for a minute.
Maybe I'll turn on my air condition because temperature is pretty high now. One second.
Yeah, well, so thank you very much, Eran. That was really a great talk, and I'm sure there are the questions. I will
Okay.
turn off the recording to, I don't know, help people decide that